Hello, everybody. Welcome back to the final abstract algebra class of the semester. I know, all good things must come to an end. Plan for today, we're going to finish off the irreducibility worksheet. My office hours, I will have office hours during finals week, but I haven't figured those out yet. It's still like almost a week ahead of Friday before finals week. Hopefully by the time you Friday's class, I'll have posted these, and if not, then I guess I have. As far as homework goes, though, by now you should almost certainly definitely have the final exam, and so that's your homework. Since this is a final class, I thought I'd give you 2 jokes instead of 1. First joke: what is the longest word in the English language? Did you say smiles? Because there's a mile between the 2 S's at the start and the end? If you said that, you're wrong. Clearly, the longest word in the English language is slight years. Yes, that's one word, slight years. Why? Because there's a light year between the S at the start and the S at the end. All right. That one, Dr. Gersel, that's too hokey for me. What's the longest acronym, then, in the word English language? Turns out that the longest acronym in the English language is recursion. Why is that? Well, if you take the R in recursion, what does that stand for? It stands for recursion. Where this R also stands for recursion. And this R also stands... You get the joke. It's a joke about recursion, okay? Anyways, let's pick things back up where we left them off last time. So, last class, we had talked about, first of all, what PIDs are, principal ideal domains, which are rings that are integral domains where every ideal can be generated by a single element. And we also talked about the difference between prime elements in a ring and irreducible elements in a ring. Where an element A in a ring is irreducible if A is not a unit, forgot to write that down, and whatever A is the product of 2 other things in the ring, one of those other 2 elements has to be a unit. In other words, anytime A is the product of 2 things in the ring, at least one of those elements has to have a multiplicative inverse. Whereas an element A in a ring is prime if whenever A divides the product of 2 elements, A divides B times C, A has to divide B or A has to divide C. And we talked about last time how you've been lied to your whole life about what prime numbers are, because the definition for prime numbers of only factors are 1 in itself that you probably learned a long time ago is actually the definition for irreducibility within the ring of integers, not primeness. And so, why do we call it that? Why have you been lied to? Is there some sort of cabal of mathematicians who've decided every school kid must be lied to? That sounds fun. I wish that was the trick. I love lying. But in any case, we proved last time that anytime you're working over an integral domain, all prime elements have to be irreducible. And the question I want to start things off with today is, does the same hold true in reverse? In an integral domain, do irreducible elements have to be prime? Turns out, well, let me write that down first. In an integral domain, must all irreducible elements be prime? Probably guess, or if not guess, you can literally see the answer in the worksheet. Turns out the answer is no. It's possible in an integral domain for an irreducible element to not be prime, even though all prime elements have to be irreducible. And in pretty much all the integral domains we've seen so far, all irreducible and prime come out to be the same thing. So I'm going to have to be a little bit sneaky here in how I come up with a counterexample here. We're going to have to look at a new ring. Ow! And the ring we're going to look at is this one, where our ring is going to be made up of real numbers plus complex polynomials multiplied by x. What the heck is that, Dr. Gerstle? So that would include, so what this ring looks like is the ring of all complex polynomials. So polynomials whose coefficients are things of the form a plus bi. F of x in the ring of all constant or complex polynomials such that the constant term of f of x is real. All complex polynomials where all the other coefficients are allowed to be things involving i's, like 1 plus I, 2 minus 3i, etc., but the constant term has to be a real number. So for instance, something like 1 plus I x squared minus 2I x plus 3 would be an element in our ring. 1 plus I x squared minus 2I x plus 3 minus I is not in our ring because this one has a constant term that is not real, whereas this one has a constant term that is real. Let's add an x cubed on, just for funsies. Every coefficient here is a complex one, and the constant one is real. Dr. Gerstle, what about the x cubed? That doesn't have a complex coefficient. Yes, it does. 1 is a complex number. It's 1 plus 0. So this is our ring we're going to look at. And for our counterexample, and I claim in this ring R, x is irreducible but not prime. Oh, by the way, R, this is an integral domain. Well, I'll leave that to you as an exercise to prove that. But this is an integral domain where we have an element, namely x, that is irreducible but not prime. So let's see if we can prove that. So if x is equal to the product of two elements, we're going to start by proving irreducible. So let's suppose x is the product of two things in this ring. So in other words, we're going to assume x is equal to the product of a plus x times f of x times b plus x times g of x for some real numbers a and b. F of x and g of x are allowed to be any constant polynomials. So we're assuming we have x as the product of two arbitrary elements in this ring, a plus x times f of x times b plus x times g of x, for some a, b real, f of x, g of x complex polynomials. We want to show one of these two things has to be a unit. So let's see if we can do that. If x is the product of these two things, well, that's going to tell us that x has to be equal to a times b plus x times f of x times b plus g of x times a plus x squared times f of x plus g of x, or f of x times g of x. That's just from FOILing this expression all out. And when we say x is equal to this hot mess, x has to be equal to this no matter what number we plug in for x. So what does that tell us? That tells us that the constant term and this x squared term have to both be 0. Actually, this term doesn't have to be 0. I take that back. This term has to be equal to 0. Why is that? Well, it's because if this term right here is not 0, then this whole expression is going to have a positive or a non-zero x squared term in it. And if it has a non-zero x squared term in it, then it can't possibly be equal to just plain old x, which does have a zero x squared term. So if x is equal to this whole thing, the expression we're multiplying by x squared has to be 0. And so f of x times g of x equals 0, which in turn is going to tell us that f of x equals 0, or that g of x equals 0. Since the complex polynomials do form an integral domain. So we know one of these two polynomials has to just be straight up 0 in order for x to be equal to the product of these two things to begin with. So we're going to say, without loss of generality, f of x is just plain old 0. Well, if f of x is the 0 polynomial, then that's going to tell us that x has to be equal to a times b plus x times g of x. So what do we know about a? A can't be 0. A is not equal to 0, since if it was 0, we get that a times b plus x times d of x would have to be 0 rather than x. So x is equal to this thing right here. Thus, we can say that a, which is equal to a plus x times f of x, since f of x is just the 0 polynomial. This polynomial right here is a non-zero real number. And hence, it has to have a multiplicative inverse and be a unit. So, in other words, to sum up, this tells us that x has to be irreducible. Because anytime x is equal to the product of two things in this ring, x, one of those two things has to have been irreducible to begin with. So we've shown that x is irreducible. Probably take note of that. We now have to also show that x is not prime. So let's see if we can do that. This one's a little bit quicker. In order to show x is not prime, what we would have to do is we would have to find some example of a b and a c in our ring such that x divides the product of b and c, but x does not divide b and x does not divide c. And here's where we have to get clever and use the fact that we're dealing with complex polynomials specifically. Would you agree that x divides 2x squared in this ring? Since 2x squared, well, that's just equal to x times 2x. So x divides 2x squared. But here's the sinister thing about 2x squared in this ring. Turns out to be the case that 2x squared we could write as 1 plus I x times 1 minus I times x. Because if you were to multiply out 1 plus I times 1 minus I, you would get 1 plus I minus I squared, which swoosh swoosh, becomes 1 minus negative 1, which is 2. So 1 plus I times 1 minus I is 2, hence 1 plus I x times 1 minus I x is just going to be 2 times x squared. So x divides 2x squared, hence thus x divides the product of 1 plus I times x times 1 minus I times x. But here's the catch. X x does not divide either of these two terms on itself. X does not divide 1 plus I times x, and x does not divide 1 minus I times x. And the main reason is because the only way for x to divide 1 plus I times x is to say x times 1 plus I is equal to this thing. And if x were to divide this thing, you could say, but x divides this, it's x times 1 minus I would give us this. But here's the catch. 1 plus I and 1 minus I are not elements in our ring. Why is that? They're not elements in our ring because they're complex polynomials, sure, but their constant terms, which they are constants, but their constant terms are not real numbers. So in other words, there's no element in the ring we can multiply x by to get to 1 plus I times x. And there's no element in our ring we can multiply x by to get to 1 minus I times x. So x divides the product of these two things, but neither of the things individually, and that then is going to tell us x is not product. So to sum up, in any integral domain, all prime elements have to be irreducible, but not all irreducible elements have to be prime. Because here's an example of an integral domain and an element x within it that is prime, or that is irreducible, but not prime. So prime, it's not prime if and only if irreducible in an integral domain. Well, that's disappointing. Fortunately, there is a class of integral domains where prime, if and only if irreducible, is true. That being these PIDs, these principal ideal domains we talked about at the front of this worksheet. So if you recall, let's erase some of this. If you recall, we said that a PID is in other words, a principal ideal domain is an integral domain where all ideals are principal. In other words, any ideal I must be equal to the ideal generated by some A, for some A in elements in our ring. And it turns out that while in an arbitrary integral domain, you can have things that are irreducible but not prime. In a PID, a principal ideal domain, all irreducible elements are prime, and so irreducible if and only if prime. So let's write that down and prove it. So here's our theory. In any PID, any element is prime if and only if it's irreducible. So prime and irreducible are logically equivalent in a PID, even though they're not in an arbitrary integral domain. Here's our proof. Prime if and only if irreducible. All right, let's go from left to right. Done. That was easy. Let's move on. Wait, why is it done? Well, we've already proven left to right because we've already shown that in every integral domain, all prime elements have to be irreducible. And since in a PID, all PIDs by definition are integral domains, that then tells us if it's prime, we already know it's irreducible by this theorem from the end of last class. So we don't need to prove left to right again. We just need to prove right to left. Let's do that. So we're going to suppose that our ring R is a PID, and that element A is irreducible. And our goal is going to be to show that that element A has to be prime. Well, the way we show A is prime is we suppose that A divides the product of B times C for some elements B and C in our ring. And then our goal is going to be to show that A divides B or A divides C. So let's see if we can do that. So that if A divides B times C in a PID, then A has to divide B or A has to divide C. So we're going to consider we're going to consider the ideal. I'm going to call it I, that's equal to the ideal generated by A and B in our ring. Which, if you recall, we said that this ideal, by definition, is the set of all elements of the form AR plus BS. This is bullshit. Where R and S are allowed to be any elements in our ring R. So we're going to look at this ideal generated by two elements, A and B. Since we're working in a PID, we know all ideals should be able to be generated by some single element. So what that tells us is that the ideal generated by A and B should be equal to the ideal generated by some single element, D. Since R is a PID, AB has to be equal to the ideal generated by D for some element D in R. Here we're invoking R being a PID. R was a PID, we'd be stuck. We couldn't do anything. So, but we know this set of elements is equal to the set of all multiples of a single element D in our ring. Well, we know that A, which you can write as A times 1 plus B times 0, we know A has to be able to be in this ideal generated by A and B. We're in a PID, hence an integral domain. So we know we have a multiplicative identity of 1. Since we can write A in this way as A times 1 plus B times 0, that tells us A is an element in this ideal. Hence, A is in the ideal generated by D, because the ideal generated by A and B is the same as the ideal generated by D. Hence, A is equal to D times T for some element T in our ring R. So this tells us A has to be the product of D, this generator of this ideal here, times some other element T coming from our ring. And here's the catch. We know, or we assume A is irreducible to start with. If A is irreducible and A is equal to D times T, what does that imply? That implies one of these two elements, either D or T, has to be a unit. Because that's what it means to be irreducible. Is anytime you're the product of two other things, one of those things is a unit. And here, we're going to have to split things up into two cases. One where D is a unit, and one where T is a unit. Our ultimate goal, remember, is to show A divides B or A divides C. This time we do have to consider the two cases separately. We can't just say, without loss of generality, A divides D, because the two cases actually do behave differently this time. So we'll first show that if D is a unit, then A has to divide B or C. And then we'll show if T is a unit, A still has to divide B or C. So here's our first case. Case 1. And that's going to be the case where D is a unit. Well, if D is a unit, then what do we know about the ideal generated by D? Well, we know D is an element in this ideal, and if D is a unit, remember, we said that anytime you're looking at an ideal that contains a unit, that ideal has to be the entire ring. This ideal contains a unit, has to be the entire ring. Hence, 1. The multiplicative identity has to be an element in this ideal. Because this ideal contains the entire ring, 1 is an element in that ring, therefore 1 has to be in the ideal generated by D. But we also know that the ideal generated by D is the same as the ideal generated by our original A and our original B. So 1 is an element in this ideal as well, the ideal generated by A and B, which means 1 has to be something of this form. We should be able to find some R and S such that AR plus BS is equal to 1. So 1 is equal to AR plus BS for some elements R and S coming from our. Don't worry, we're getting somewhere. Because the next thing we're going to do is we're going to multiply both sides of this equation by C. And that'll tell us that C is equal to, C times 1 is equal to C times AR plus BS. So in other words, that C is equal to CAR plus CBS using the distributive property. Or if you prefer, it's equal to, I need to use my notes here for a second, A times CR plus BC times S. Where here, I'm using the fact that we're working in an integral domain, so multiplication is commutative. And since we're working in any ring, it's multiplication is associative, so we can play around and rewrite this term CAR as A times CR, and we can rewrite this as BC times S. And I'm choosing to write it this way for a very specific reason. Why am I choosing to write it this way? That C is equal to A times CR plus BC times S. Well, the reason is we know that A divides the first term in the sum, A times CR. That's because A times CR is equal to A times CR. And A has to divide BC times S, where that one comes from the fact that A divides BC. Since A divides B times C, which we assumed from the start, that tells us A has to divide BC times anything else, so BC times S. Since A divides the first term in this sum, and since A divides the second term in that sum in the bottom right, thus, A has to divide the sum of these two things, A times CR plus BC times S. But what is this sum equal to? It's equal to C, hence A divides C. So that's our first case. Then we showed that in the case that D is a unit, A has to divide B or C. Specifically, we showed that A has to divide C in this case. So let's consider our second case now. This is a little bit shorter, I think. Our second case is the case where T is a unit. Way back when we said A has to be equal to D times T. Oops, I forgot to write this out. Thus, since A is irreducible, D or T must be a unit. Sorry about that. So if T is a unit, what can we say about this? Well, then we know that the ideal generated by A has to be equal to the ideal generated by d times t. Why is that? Well, we assume A is equal to d times t, which I claim is going to be equal to the ideal generated by t, or by d. And this is going to be an exercise. This is a good exercise. I should put this on the final now that I think about it. I'm putting this on the final, if I remember to. That if t is a unit, then the ideal generated by d times t has to be the same as the ideal generated by d. That multiplying d by a unit doesn't change the ideal that d generates. But Dr. Gerstle, if you have a unit in your ideal, doesn't that have to be the whole ring? Yes, but we didn't necessarily say that t itself is an element in this ideal. We just know that this is the ideal generated by d times t, which may or may not include the element t in it. These two are the same, I claim, because t is a unit. And I'm going to try and put that question on the final for you. So what do we know about the ideal generated by d? Well, that tells us we know already that the ideal generated by d is equal to the ideal generated by a and b, and that's by assumption. We said d was specifically chosen so that the ideal generated by d was equal to the ideal generated by a and b. We knew a d like that had to exist because our ring is a PID. So now we know that the ideal generated by A is equal to the ideal generated by A and B. Well, then we can say, since B is an element in this ideal generated by A and B, that tells us B has to also be in the ideal generated by A, because the ideal generated by A and B is the same as the ideal generated by A. And thus, B is equal to A times R for some element R in our ring. So A divided B. So in other words, either way, whether D is a unit or T is a unit, we just showed that A has to divide B or C. If D is a unit, then A had to divide C. If T is a unit, A has to divide B. But either way, we showed that if A divides B times C, that A has to divide B, or A has to divide C, and therefore A has to be prime. Thus, in either case, let's just kind of sum up what I just said. A divides B, or A divides C, hence A must be prime. And there's our proof. We showed that all irreducible elements, we started with the assumption A is irreducible, and proved A had to be prime. And last class we showed that in any integral domain, including in PID specifically, prime elements have to be irreducible, and thus prime if and only if irreducible. So where does that leave us in terms of the web of lies that your teachers have been developing all these years? Well, it's kind of okay, because since the integers are in fact the PID, any integer A is prime if and only if it's irreducible. So you might then think to yourself, well, maybe it's okay then, our teachers have been lying to us about the integers. Yes, they did give us the definition for irreducible and called it prime, which they shouldn't have. But prime and irreducible integers happen to be the same thing within the ring of integers, so maybe it's okay. The issue, though, is that in the larger, that just because in the ring of integers, irreducible and prime mean the same thing, doesn't mean that holds true in all rings. There are a lot of rings out there where you can have prime elements that are not irreducible. So is that okay? I don't know. I should make that a question on the final. What's your opinion on the matter? Coming up with all sorts of final questions that do against you. All right, that's going to do it for this class. There may be a special bonus video. I may have lied to you. We'll see if I have time to put one together for a special topic at end of the week, end of the semester. But if not, it's been great teaching this class. Sorry we had to go online. Much prefer teaching this in person. You all are a great group to work with for the most part. And I hope you all have a safe winter break, finals go okay, that you stay healthy and such. Please let me know if there's anything I can do to help, or if you just want to talk, or life sucks and you need someone to vent to. Have a good one. Watch out for snakes.